Okay, we got question 3. Satellite is in orbit 800 kilometers above the surface of the Earth. The surface of the Earth has a radius of 6,400 kilometers. At this distance, the acceleration on the satellite is 8.28 meters per second squared. What is the speed of the satellite? Okay, so we're looking for linear speed. Okay, so let me draw this out because a lot of students get this one wrong. With the radius of the Earth, they don't account for. Radius of the Earth is 6,400 meters, and then this satellite is another 800 kilometers outside of that. And there's our satellite circling or orbiting the Earth at that great distance. Okay. Now, we know that the distance, at this distance, the acceleration on the satellite is 8.28 meters per second squared. The reason it has that acceleration is our centripetal force that we're feeling around the satellite. So if I have AC, or centripetal acceleration, I know that's v squared over r. Okay. And that's what I'm looking for is our velocity. The radiuses were given and acceleration was given. So I'm going to have an 8.28 for our acceleration. V squared is what we're going to solve for. And the radius is where everybody goes. We need 6,400 plus the 800. So we're going to have 7,200. 7,200 kilometers. So that's times 10 to the third meters. Okay. So now to get velocity by itself, you're going to multiply this on both sides. That'll cancel it from here. And then we'll take a square root of the entire thing in order to get velocity by itself. Okay, so we'll do 8.28 multiplied by 7,200 times 10 to the third. And then finally, we're going to take a square root of our answer. And we get that V, if we did it all out correctly, should be 7,721. And that's going to be meters per second because it is a velocity. So there's part A, the speed of our satellite. Part B, what is the period of the satellite to make one revolution around the Earth? Okay, so how long does it take to get all the way around? Well, I know that a period is the amount of time it takes for one full revolution. Okay, so we get from period, if you need a catch up here, we get that our omega is our change in theta over change in time. Okay, omega means our change in theta. Well, if I want to go a full theta of 2 pi, it means one full revolution. The change in t for one full revolution is a period, t. And then if we solve for t, that means I'm going to get 2 pi over omega for a period. Okay. So, if we are looking at a period here, we're going to go ahead and have 2 pi, and then to get to w, I don't have the radial speed, but I have the velocity, and I know that the velocity is equal to r omega. Okay, so if I work this backwards for omega, I know omega then is equal to v over r. If I plunge in omega is equal to v over r, I'm going to get v, I'm going to get r up top. Okay? Because the fraction flips when it's in the denominator. So if that's the case, I'm going to have 2 pi times 7,200 times 10 to the third, or you could just add 3 more zeros for 7,200,000. And we'll divide that by the velocity 7721. Okay, so let's see what that gets us. 2 times pi times 7,200,000, and divide that by 7721, our previous answer. And we get 58.59. And this is in seconds, right? Because it's a period, so it's standard units. This is in seconds. If you did want to convert that into days, or minutes rather, you get about 98 minutes. Might be a little bit easier to realize that it's less than 2 hours, about an hour and a half, and it completely does a circle around the Earth. So it is moving quite quickly. That's our answer here for part B.